Monday here. Yeah, you're fine. It's just right here. Yeah. But you're going to go that way?
Yeah.
Yeah, that's better. All right, so here we go. This is just reviewing exponential functions. Tomorrow we start to graph them. We get a little more information. But today, this is a bit of a reminder when you're dealing with these problems. An exponent to a power of a power, we just multiply them together. Okay, that's going to happen in these problems. But to start, this is our general form. And essentially, this form is the same as my exponential rate of change. There's slight differences. A is always the initial value. A is always the initial value, what you're starting with. Because these equations, they aren't like a linear equation where you start with one, you go up one. You start with one, you go up one. It's not going to grow in that way. It's going to grow either faster or decay faster. So instead, it's going to start off like this, and then it starts to grow really quick. It's really just kind of like the second half of a parabola, but we get some different things that go on with this, where we're going to end up with, equations like this that go close to an asymptote, and they kind of get closer and closer without ever touching. Okay. That's tomorrow. We're going to get into that. But here, if we're just doing general form, f of x, function notation, that's our output, our y value, initial value a. The base is just b, input of x, vertical shift of k. Now remember, in a couple weeks, we're going to get to vertical shift. Here's my parabola. If I have a vertical shift, it's just moving it up and down. If h is different, it's moving it side to side. If other elements are different, it's either compressing it or stretching it. And it can compress or stretch in both directions as well. Those are the main three things that we're dealing with. Okay. So I'm setting it up with the general form, so when we get to transformations, you'll be able to kind of navigate that a little easier. Okay. So this is for reference. Mainly what we're doing today is this: finding those exponential equations based on your rate of change. So let's see. Have we talked about this in here? Okay. Does anybody know what happened with rabbits in Australia? Do you think rabbits are native to Australia? Well, they are not native to Australia. So you know that England in their colonial conquest, like all the European countries, just said, hey, this huge continent of Australia is mine now. Nice. Crazy move. So they did that, and they ended up making Australia actually like a prison colony. And they would send all their prisoners to Australia. And that's how like Australians have like a personality of just being kind of like a little deviant. It's like a little bit like rougher. So one of the people that came to Australia brought like 5 bunnies. 5 bunnies. And the bunnies started to repopulate. They got out, they left, and they repopulated in the wild. And within like 100 years, they had this huge inundation of bunnies where there were millions of bunnies in regions, right? Now, how the heck did that happen? How did we go from 5 bunnies to millions of bunnies? What do we know about bunnies? They reproduce quick, right? They can have a new litter every like couple months. It can happen really quick. So one bunny, pair of bunnies can make like 8 different bunnies. And then what happens to those 8 different bunnies? They come to age, like within like 3 months, 4 months. What do? Each of those 8 bunnies have 8 more bunnies. But not together, because that's incestual. Well, that might have happened, because they started from 5. They started from 5.
But there was 5, so technically, like,
you could do it. We're going to do that, Unit 4, we're going to do that, permutation combinations and sequences.
Okay.
Just pull your beanie down. So bunnies have a very fast growth rate. That's going to be an aspect of growth. Okay. Who could think of an aspect of where something decays, where it gets smaller and smaller, maybe never gets to 0, but it decays? What's like an example? Who could think of one? What do you think? What decays?
Well, now that gets to things like extinct animals, like population decreasing,
That's good. Yeah, population decreasing. In second period, somebody said like the bubonic plague, right?
cockroaches.
Right. Some squirrels do.
Oh my gosh.
Watch out for squirrels. You're like, I'm never going to the forest again. No, just some do. Okay, so decay might be the decay of a population due to disease, decay of radioactive elements, uranium decays, losing electrons, it decays in its mass. Things like that are decay, and they're going to look, instead of growing up, they're going to grow down towards zero, but never quite touch it. So these are abstract ideas. Okay. Now here's the deal. When we have, this is the main difference right here. This is what we're going to focus on right here. Within the parentheses is our growth or decay factor. The growth or decay factor, you know, if it's greater than 1, it's going to grow. Because if I have a number and I multiply it by a number greater than 1, it gets bigger. If I have a number and I multiply it by less than 1, actually I should say less than 1, and you know, I'll actually just say decimal. Why don't you put it this, decimal. So it's between 0 and 1. It's just a decimal. If you have a decimal, then we end up getting smaller and smaller, right? Multiply a number by a decimal, you get a smaller number. So that is going to distinguish if it is a growth or a decay factor. And from that, once we know that, then we can figure out what the rate is. Okay, so let's give a real example, because right now you can see the faces. You guys are giving me different faces. All kinds of faces out there. Look where we just learned to look. Where do we look to see if it's a growth or a decay problem? Where do you look? Do I look here? Out here? Right there? It's right in there. So is this one growth or decay? It's growth. It's growth because it's greater than 1, so it's growth. Okay. So we know it's growth. Let's find the rate now. Because it's growth, I know that it is. Do you think it's the 1 plus r or the 1 minus r for growth? 1 plus r, right? So again, this 1.25, it was found out by putting in some rate as a decimal, and adding it together. So watch what I can do. I could say, well, the 1 plus r, because I know it's growth, that's equal to 1.25. Subtract 1. You don't have to do this unless you need to, because you can get to where you deduce that out pretty quick. What is this as a percentage? 25 cents is 25% per 100. So I know that this is, what is the rate? It's 25%. It's growth. What is the initial value of this? What's the initial value, though? 0.2. This is our A value. That's always our initial value. So we have 0.2. Okay. Can we do that? I want to do one exactly like that, actually. Not go to the next one yet, because I need everybody to tell me what you think about that. Do the same 3 questions. What is the rate? Is it growth, decay? What's the initial value? And then show your neighbor. Okay, we're just introing, getting used to working with these again. All right, so essentially we have this problem. I'm going to call in some random folks. Let's see. Tommy, what is this growth or decay? How do you know? Good. This is greater than 1, so I know it's growth. Perfect. All right, let's see. All right. Rhea, help me out. Can you tell me what the rate is? 1%. 1%. How did you know? You know it's growth. So you say, well, what did I add to 1? What did I have to add to 1? Because the growth is 1 plus r. The decay is 1 minus r. So what did I add to 1 to get 1.01? Your rate is 0.01 or 1%. Right? Okay. Initial value, Omar, help us out. 5. So if you start with 5 bunnies, you have a growth rate. That's not a bunny growth rate. That's like that's not even countries have 1%. 2% growth rate's better.
It's like the plant that's like growing.
That's it. Maybe it's really slow. It's like how elephants have one new elephant every few years, and it takes like 12 months for it to, pregnant. Okay, so we'll go with elephants. 5 elephants. If they triple every decade or something, then I would plug in how many decades I have. I'd be able to apply that, then multiply it by 5. So we can do these on a calculator. The programming for it isn't so tricky. Let's just try one more right here. All right, looking at this problem, I want you to find growth or decay, what's the rate, what's the initial value, and then let's practice plugging in g of, T. How about g of 4? I want you to then figure out what g of 4 is. All right. Stop rattling. All right. Check with your neighbor if you're done. Check with your neighbor, see if they have the same idea.
I know.
Okay, if you don't put in the first, it will be decay, but if you put in the 4, it will be April.
Yeah, that's 3. Who's having a little trouble with this? The g of 4? Finding the g of 4? Maybe that's hard, maybe not. All right, let's answer this one together. Is this growth or decay? Decay. Let's see, Davis, how do you know it's decay? It's less than 1. So if it is, looking at our growth decay problem here, it must be the 1 minus the rate because we have less than 1. You must have subtracted something. So I like that, decay. And what is my rate of decay? Anais, what do you think? 0.05. And if I said that as a percent, what would that be? As a percent, what do you think? Yeah. If you forgot, you just move it 2 places. That's how we find the percentage conversion. Let's see. Let's all say the initial value together. What's the initial value? 3. Pretty quick to see that's up front. It's the A value. And then how about g of 4? Let's go ahead and plug that in. 3 times 0.95 t over 2. So that's 4 over 2. 3 times 0.95 raised to the 2nd power. Because 4 divided by 2 is 2. I don't know what that is. But somebody can magically give me the end answer, and I'd be appreciative. How much? 1.9?
No, oh wait. 6.7.
1.96.
No, 6.7.
1.67?
6.7.
It's just 6.7.
Yeah.
All right, cool. Thanks. Anybody else get 6.7? Yeah? Oh, you didn't do the last yet. Okay. So with that, I would take this value, 0.95. I'd square it. Get your answer. That's done. And then multiply it by 3. Let's see what we get. Nice. That's plenty of time. Okay. Times 3. Yeah, I got 2.707. 2.707. So we'll change that up. Maybe double check that works, see where you got that, where you missed that part. 2.7075, so we'll go 0.8. I would take 2.71. Okay, what do you guys think? Thumbs up, sideways, down for this. Can we do it? Yeah, the homework for this is very direct. Tomorrow's when we get a little trickier. I just want you to come in with that mindset. Tomorrow's a little trickier. All right, I'm just going to tell people, subscribe or else. There's no real threat to that.